In our fast-paced, technology-driven world, efficiency is key. Whether you're a seasoned developer or just starting out, optimizing your code for speed can significantly impact the performance of your applications. In this series, we'll explore various strategies and best practices to enhance your coding efficiency. From algorithm optimization and effective use of data structures to leveraging modern tools and profiling techniques, we'll cover a range of methods designed to help you write code that runs faster and performs better. Let's dive in and unlock the secrets to writing blazing fast code. Welcome to Make Your Code Faster. Make your code faster. Reusing complex calculations. In the ever-expanding realm of big data and resource-hungry applications, optimizing your code for peak performance is no longer just about speed. Efficient code translates to lower power consumption, a critical factor for battery-powered devices, massive server farms, and eco-conscious development practices. While intricate algorithms and ingenious data structures have their place, sometimes the most impactful improvements can come from seemingly simple tweaks. Today's episode dives into a powerful technique, reusing complex calculations, that can significantly enhance the speed and power efficiency of your code, particularly when working with massive datasets. This code shows two ways to calculate the density of a gas cloud at various points in space based on input parameters. The first function calculates the density directly, while the second function optimizes the calculation by pre-calculating reusable parts of the formula, potentially improving performance. Both functions iterate over the grid points, calculate the concentration using a Gaussian distribution, and convert the concentration to density using a given function. The first function, Create Gas Cloud Density Array, calculates the density of a gas cloud at various points in space. It takes two parameters, gas cloud input data and an empty three-dimensional density array. The gas cloud input data is a struct that contains information about the gas cloud, such as its initial conditions, dimensions, and properties. Density array is a 3D array that will store the calculated density values. The logic. The function first initializes variables for the maximum dimensions of the gas cloud. Then it iterates over each point in the 3D grid, calculating the density at that point using the following steps. Calculate sigma y and sigma z. The function calculates the standard deviation sigma e and sigma z based on the current x coordinate using the sigma y and sigma z functions. Calculate the concentration. The function calculates the concentration at the current point using the Gaussian distribution formula. The formula takes into account the distance from the center of the gas cloud, the standard deviations, and the initial concentration of the gas. Calculate the density. The function converts the concentration to density using the calculate density function. The conversion depends on the specific properties of the gas. Store the density. The calculated density is stored in the density array at the corresponding index. In summary, the Create Gas Cloud Density Array function calculates the density of a gas cloud at different points in space. It takes input data about the gas cloud, such as its initial conditions and dimensions. The function then iterates over a three-dimensional grid, calculating the concentration at each point using a Gaussian distribution formula. Finally, it converts the concentration to density using a specific conversion function and stores the results in an array. The primary difference between the two functions lies in their approach to calculating the concentration. The first function, Create Gas Cloud Density Array, calculates the concentration directly for each point in the grid. This involves recalculating certain parts of the concentration formula for every point, which can be inefficient, especially for large grids. The second function, Create gas cloud density array with reuse optimizes the calculation by pre-calculating reusable parts of the concentration formula outside the inner loops. This avoids redundant computations and can significantly improve performance, especially for large grids or computationally expensive concentration calculations. In this example, we are around 50% faster than the first function. Here's a breakdown of the differences and their impact on performance. The first function, create gas cloud density array, calculates concentration directly for each point in the three-dimensional grid. It recalculates most parts of the formula repeatedly and will be inefficient for large grids or complex concentration calculations. This function, create gas cloud density array with reuse, pre-calculates the reusable parts of the formula outside the inner loops so that it avoids redundant computations. In summary, the second function is generally more efficient and performs better than the first function due to its optimization of the concentration calculation. The performance improvement can be significant, especially for large grids or computationally expensive concentration calculations. The Create Gas Cloud Density Array with Reuse function offers several benefits over the original Create Gas Cloud Density Array function. Improved performance. By pre-calculating reusable parts of the concentration formula, the function avoids redundant computations, leading to faster execution times, especially for large grids or complex calculations. Increased efficiency. The optimized approach reduces computational overhead, making the calculation more efficient and allowing it to complete in less time. Reduced resource consumption. The pre-calculation can potentially reduce the overall resource consumption of the algorithm, such as CPU usage, memory requirements, and power consumption. Summary. The Create Gas Cloud Density Array with Reuse function is a more efficient and optimized implementation for calculating the density of a gas cloud. It achieves this by pre-calculating reusable parts of the concentration formula, thereby reducing computational overhead and improving performance. This optimization is particularly beneficial for large grids or complex calculations where the original function might be inefficient. Additionally, the optimized approach can potentially lead to reduced power consumption, which is important in energy-sensitive applications. Thanks for watching this episode about Make Your Code Faster, reusing complex calculations. Feel free to reach out by email if you have any questions. Next episode is about the art of data structure selection. See you in the next video.